Hey friends, it's good to be back with you. Today it's time to start on Fourier transforms. Now in the last two videos, I went over Fourier series. Now the mathematical entity you're going to see most often that's associated with Fourier is the Fourier transform. And that appears in two different forms. One is an integral transform, which I'll go over here in a second. And the other one is the discrete version that appears in computer software called the discrete Fourier transform, or much more often, the more efficient version of it is called the fast Fourier transform, or just FFT. And you'll see the phrase or the name FFT everywhere. I've even heard it used as a verb occasionally, which I don't agree with. But you'll see that algorithm everywhere. If you burrow into Excel, of all places, Excel has an FFT algorithm in it. Now, it's really hard to use. I mean, you really got to want it to go into Excel. MATLAB is really good at Fourier transforms, and they're implemented in a robust way that's very powerful and pretty easy to use. So I'm going to, when we go to the computer here in a little bit, I'm going to show you how to do this first in MathCAD. I'm just going to do the integrals there, and then we're going to spend some time learning the syntax in MATLAB. So first things first, where does the Fourier transform come from? Well, if you remember, these are the this is the definition of coefficients for the Fourier series, the complex Fourier series, where, let's see, n is an integer, and omega is right there. I'm going to call this omega naught for right now. This is 2 pi over t. So we know if we evaluate this integral, we'll get c sub n. If you want, people noticed fairly early on that you could plot n omega naught if you want. There's n omega naught right there. And maybe this is the absolute value of c. And I'm using absolute value because we expect this to be complex. Well, what do you get if you do this? Well, you're going to get C0, C1, C2, and it's going to be symmetric about the vertical axis here. It's going to go the other direction too. I'm only going to draw the positive omegas, but the negative ones do exist. So you could plot them. Oh, it doesn't look too good. Hang on. Like that if you wanted. And maybe put a little dot on there just to show that this is a point we're plotting. Okay, that's the amplitude there. And so this is what this could look like, where that's omega naught, that's 2 omega naught, 3 omega naught, and so on. All right. Well, what if you want better frequency resolution, or maybe a more precise way to say this is better localization in frequency? Well, I want omega naught to be smaller. If omega naught was smaller, these bars I've got would be closer together, and this would look more and more like a continuous distribution. Well, there it is. How do I make omega naught smaller? Well, I make t bigger. So instead of integrating across one period, maybe I could integrate across a couple. Yeah, you could do it that way if you wanted. That's kind of a kludge. Let's see if we can figure out another approach. Well, a better one is to say, what happens about with these upper and lower integration bounds at t over 2 and minus t over 2? This is how it usually appears in the books. Well, what if I let that get bigger? How big? Well, could it approach infinity? Yeah, it could. The problem is, as t approaches infinity, 1 over t approaches 0, and c of n approaches 0. That doesn't seem like that's getting us anywhere. Well, one algebraic change fixes it. Now I've changed two things here. I multiplied through by t, which you wouldn't think would do much, but it does. As t goes to infinity and this goes to 0 as t goes to infinity, the product of the two of them goes to some non-zero finite value. And as we do this, this becomes f of omega. That's the Fourier transform. Now, one more little piece of sort of bookkeeping here. N omega, as omega naught goes to 0 because this is getting bigger, n omega becomes omega. This becomes a continuous function of omega. So this is the Fourier transform. And it follows that same pattern as integral transforms that we saw a couple of videos ago. There's f of t, and there's some kernel function. Here the kernel function is e to the minus I omega t. So this is what a Fourier transform integral looks like. The nice part about this, since I'm integrating from positive to negative, negative to positive infinity, I guess, this works on aperiodic signals. What's an aperiodic signal? Well, it's something that doesn't repeat itself. So what about an impact function? Let's say I've got a hammer and I hit something and I'm measuring the force on the hammer. There are force sensing hammers in most test labs, most mechanical test labs anyway. That impulse happens and then it never happens again. There's nothing, 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 bang, and then that's it. What if you're landing an airplane on a runway and you land hard, or maybe landing on an aircraft carrier where you land really hard? There's nothing, 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 bang, there's this giant force, and then there's nothing. Okay? That's an aperiodic signal. All right, so the signal you're working on, f of t, doesn't have to be periodic anymore, and that's big. All right, this is the big idea behind it. Let's go over to my computer, and we're going to do this in 2 steps. I'm going to go on MathCAD, show you how the integral works, and then we're going to go in MATLAB. We'll evaluate the Fourier integral, but more specifically, I want to show you some of the algorithms that appear in MATLAB that get used all the time for frequency transforms or representing time domain signals in frequency domain. There's a couple of them you're going to want to know about.